the compound live stream. Anyone to access this can be watch, share others. Thank you. So category. Here the definition. A subset of metric space is said to be first category if it can be of first category. It can be written as union of. It can be written as union of. What we are discussing today? Unit 4. Unit 4. What is the unit for? Linear transformation. Linear transformation. The last unit we discussed about the properties. What are the properties? The transformation T. The transformation T of n normal linear space 2 into another normal linear space n dash. Dash is called linear transformation. If it is a linear, you have to satisfy the following axioms. What are the axioms? First axiom, T of x plus y equal to T of x plus T of y. Now, second axiom, axiom or property or rule or postulates all are same thing. So here T of alpha x, alpha is outside T of x. Okay, already we discussed the properties of this thing. So we are now in this chapter. We are discussing 4 vital theorems. What are they? This is the first various category theorem. So already in the previous students, already you learned in the previous year in real analysis various category theorem. So this is came in operator theory also the same way. Proof is okay. Next open mapping theorem and closed graph theorem and uniform bounded theorem. Maximum 4 are the most important theorems in this chapter. Now today we are discussing about 4 theorems in this chapter. So first unit 1, 4.3 definition. What is the definition? Before proving Bayes category theorem, we need to discuss small definition. A subset of metric space is said to be first category if it can be written as union of countable family of nowhere dense sets. Nowhere dense sets. A subset of metric space is said to be metric space is said to be of second condition second category. Second category. If it is not first category, it is not first category. So now we'll go to theorem 4.3.1 Bayes category theorem. RAS category theorem. Bayes category theorem. So statement, if complete metric space is the, if a complete metric space, complete metric space so complete metric space is the union of sequence of its subsets, is the union of a sequence, union of sequence of its subsets, then the closure of at least, then the closure of at least one set in the sequence, must have non-empty interior, non-empty interior. So now clear the canvas. Proof. Let A and be a sequence of sets. Let A and be a sequence of sets. Can be a sequence of sets in the metric space X. In the metric space X. Metric space X. Such that X equal to, capital X equal to union of N, A, N. Let us suppose that, interior of AN, that equal to null set, where N equal to 1, 2, so on. Right? Here interior of A denotes the interior of set A. This meaning interior of set A. That is each AN is. Each AN is nowhere dense subset of X. Nowhere dense subset of X. Nowhere dense subset. Since X is open, X is open. So X is open. A1. X is open. A1. Is nowhere dense. Nowhere dense. by the above remark. By the above remark. Above remark. We can find an open sphere S1. We can find an open sphere SP, open sphere S1 of radius less than 1. Radius less than 1. Less than 1. Less than 1. Which is disjoint from A1. Which is disjoint from A1. Disjoint from A1. Disjoint from A1. Let us consider concentric closed sphere. Let us consider concentric closed sphere. Closed sphere F1, whose radius is half of the radius. Whose radius is half of the radius. Half of the radius. Half of the radius of S1. Of S1. Now, interior of F1. Now, interior of F1 is open and A2 is open. And A2 is now nowhere dense. Is nowhere dense. Nowhere dense. Hence, interior of F1 contains, hence, interior of F1 contains, interior of F1 contains an open sphere S2. An open sphere S2. Whose radius is less than half. Whose radius is less than half. And disjoint from A2. And disjoint from A2. Disjoint from A2. Again, consider concentric closed sphere. Again, consider concentric closed sphere. Closed sphere. Concentric closed sphere. F2, whose radius is half of the radius of S2. Whose radius is half of the radius of the radius of S2. S2. The radius S2. Now interior F2 is interior F2 is open and A2 is nowhere dense. Is open. A2 is nowhere dense. Nowhere dense. Now clear the board. Nowhere dense. Is open and A3 is nowhere dense. So as above, we can find open sphere as above. We can find open sphere. Open sphere. S3, whose radius is less than 1/4, whose radius is less than 1/4 and disjoint from A3 and disjoint from A3, disjoint from A3, continuing in this way, continuing this in this way, continuing in this way. Continuing in this way. Continuing in this way. We get sequence. We get sequence. We get sequence. We get sequence. Fn. Fn. We get sequence Fn of closed sets of X. Of closed sets of X such that D of Fn tends to 0. Here D of Fn, F of denotes the diameter of the set Fn, meaning diameter of the set Fn. Since X is complete, X is complete by the Cantor intersection theorem. By the Cantor intersection theorem. Intersection theorem. The Cantor intersection theorem. Cantor intersection. It follows that. Intersection of F of n is not equal to pi. Let X belongs to intersection of Fn. Subset are equal to capital X. But by the construction of sets of Fn, X is not in any one. X is not in any of the sets. Any of the sets. An, where n equal to 1, 2, so on. Thus we obtain an element. Thus we obtain an element. X belongs to capital X such that X does not belong to union of area that equal to X, which is contradiction. Which is contradiction. Which is contradiction. Hence the theorem This completes the proof of the theorem. So now clear the whiteboard. Next, open mapping theorem. Next theorem is open mapping theorem. Before going to open mapping theorem, lemma is most important, key to the open mapping theorem. That statement I will discuss. So, open mapping theorem 4.4. Key to the proof of open mapping. The open mapping theorem is obtained by Banach in 1929. Now, here let us x, comma r means x is the center or with the radius. The sphere whose radius is r and center x. And SR denotes the sphere of origin of the center. So it is the lemma. 4.4.1 lemma. Lemma of open mapping theorem. Open mapping theorem. So we'll discuss statement. What is that? Let B and B dash B two Banach spaces. B and B dash B two Banach spaces. Banach spaces. If T is continuous linear transformation, if T is continuous linear transformation, of B onto B dash, B onto B dash, then the image of each open sphere, then the image of each open sphere SR in B contains an open sphere SR dash in B dash. So 4.4.2. Proof is due as homework. This open mapping theorem. Open mapping theorem. Statement. What is that statement? If B and B dash are two Banach spaces, if B and B dash are two Banach spaces, Banach spaces, and T is a continuous linear transformation, and T is continuous linear transformation of B onto B dash, then T is an open mapping. Oh. We now show that T of G is open. We now show that T of G is open in B dash is open in B dash. Whenever G is open in B, whenever G is open in B, G is open in B, open in B. That is to prove the every point of G. That is to prove that every point of TG, point of T of G, is an interior point of TG, is an interior point of T of G. Now clear the board, clear the canvas. Interior point of T. Let Y belongs to T. Let Y belongs to T of G. Then there exists X belongs to, then there exists X belongs to G such that Y equal to T of X, such that Y equal to T of X, T of X. Now X belongs to G. Now X belongs to G. X belongs to G. G is open. G is open. G is open. So there exists an open sphere. Open sphere. Yes, X comma R such that yes, X comma R subset are equal to G. Since yes, X comma R X plus SR, it follows that Y plus T of SR equal to T of X plus T of SR, that equal to T of X plus SR subset are equal to T of G. By the lemma 4.4.1, just now only discussed statement, proof yes, you do as a homework. So it follows that there exists S greater than 0 such that S of S, S dash of S subset are equal to T of S of R. So that is Y plus S dash S subset are equal to Y plus T of SR subset are equal to T of G. That implies S dash of Y, Y comma S subset are equal to T of G. This shows that Y is an interior point of TG. This shows that Y is interior point of T of G is a point of D. Y being arbitrary, it follows that Y being arbitrary, Y being arbitrary, it follows that Y being arbitrary, it follows that T of G is open. T of G is open. This completes the proof of theorem. This completes the proof of theorem. This completes the proof. So now clear the board. Next, closed graph theorem 4.5, closed graph theorem. Before proving closed graph theorem, just definition we'll discuss. So closed graph 4.5. So 4.5. Whiteboard 4.5. Closed graph theorem. Closed graph graph theorem. Theorem. So explanation part of the theorems I'm shading here. Like a whiteboard I'm shading here. Explanation part. You're recording this. Okay. So definition, closed graph theorem. Before proving closed graph theorem, we need to so two Banach spaces. Yeah, two Banach spaces. B and B dash. Define a metric D. On the product space. So on the product space. B cross B dash as follows. So explanation part of I'm sharing follows. D of means inner product space of x1 comma y1 comma x2 comma y2, that equal to maximum of norm x1 minus x2 comma y1 minus y2 y2. Who can see what you are shared here? Students will see when they need. When they have time, they will open and see this. Y1 minus Y2, where X1 comma X2 belongs to capital B and Y1 comma Y2 belongs to capital B dash. So let us define the graph of linear transformation. Let us define the graph of linear transformation. Graph of linear transformation P of B into B dash of B into B dash as follows. G of T equal to X comma T of X such that X belongs to B. X belongs to B. G of T is A. That is, G of T is subset of subset of the product space. B cross B dash. Now let us prove the property. Closed graph theorem. Clear all documents. So 4.5.1. So 4.5.1. The closed graph theorem. The closed graph theorem. Closed graph theorem. If B and B dash are Banach spaces, and if T is a linear transformation of B into B dash, then T is continuous if and only if its graph is closed. Graph is closed. So graph is closed. Its graph is closed. Its graph is closed. Its graph is closed. Graph is closed. So proof of this theorem. First, we prove that graph of T is closed. First, we prove that graph of T is closed whenever T is continuous. Whenever T is continuous. Whenever T is continuous. Let Xn is sequence the graph G of T such that Xn comma T of Xn tends to X comma Y belongs to B cross B dash. That is B of inner product of Xn comma Txn comma X comma Y equal to maximum norm of Xn minus X comma norm of T of Xn minus Y tends to 0. That implies that so now Xn minus X tends to 0 and now Txn minus Y now tends to 0 as n tends to infinity. Since T is continuous, it follows that Xn tends to X. That implies T of Xn tends to T of X. Now T of Xn tends to Y and T of Xn tends to T of X by the uniqueness of the limit. Uniqueness of the limit, we have Y equal to T of X. We have Y equal to T of X. Thus G of T is closed. Conversely, assume that G of T is closed. We show that we show that T is continuous. Define B1. Linear space B with new norm. So norm of X 1 equal to norm x plus norm of t of x. Norm of t of x. That is B1 is normal linear space. Normal NLS means normal linear space. Normal linear space. We now show that B1 is also complete. We now show that B1 is also complete with respect to the new norm. Let Xn be a Cauchy sequence. Let Xn be a Cauchy sequence. So clear the board. Cauchy sequence. Cauchy sequence. Send the Cauchy sequence in B1. Then by definition of the norm. Definition of norm. Mod x, norm x1. It follows that xn, t of xn also Cauchy sequence. So Cauchy sequence in B and B dash. Respectively. Since B comma B dash are complete, it follows that there exists x belongs to B, comma y belongs to B dash, such that xn tends to x, comma t of xn tends to y. Now xn minus x1 that equal to norm xn minus x plus t of xn minus x norm that equal to norm xn minus x plus norm t of xn minus t of x that equal to norm xn minus x plus t of xn minus y tends to 0 as n tends to infinity. That is norm of xn minus x tends to 0 as n tends to infinity. This implies that B1 is complete. complete. Since norm T of x less than or equal to norm of x plus norm of T of x that equal to norm of x1. It follows the T is bounded and hence continuous mapping B1 into B dash. It follows that T is bounded and hence continuous mapping of B1 into B dash. B1 into B dash. We can show that B1 and B have the same topologies. Then it follows T is continuous in B. Then it follows T is continuous. Continuous on B. Now clear the drawing. Consider the identity mapping of I. For consider I is continuous transformation. Is continuous transformation. Of B1 onto B. This mapping I is clearly capital I is clearly continuous since I of x that equal to norm of x plus norm of x that equal to norm of x 1. Since I is continuous linear transformation, continuous linear transformation of B1 onto B. B1 is homeomorphic to B. B1 is homeomorphic to B. Hence, B1 and B have the same topologies. Consequently, T is continuous on B. This completes the proof. Okay. This is the closed graph theorem. So now clear. So uniform bounded theorem. Next. Uniform bounded theorem. Uniform bound. 4.6.1. Uniform bounded theorem. Uniform bounded theorem. Uniform bounded theorem. Let statement. Uniform bounded theorem. Statement is let B be a Banach space. Banach space and N Banach space and any normal linear space. Normal linear space. If P of I is non-empty, set of bounded BDD means bounded linear transformation of B. Linear transformation of B into N. N means normal linear space, having the property that T of Ix is a bounded subset of N. For each vector X in B, then the norm of Ti is a bounded set of numbers that is T of I is bounded subset of B comma N. Proof. For each positive integer N. For each positive integer N is positive integer N. Define set Fn. Define set Fn as follows. Fn equal to x belongs to such that T of I x now less than or equal to n for all I, that equal to Ti whole inverse minus n comma n. Then Fn is closed subset of B. Is a closed subset of B for each n equal to 1, 2, so on. Let xk be a sequence in Fn. be a sequence in Fn. Be a sequence in Fn. Be a sequence in Fn such that xk tends to x belongs to B. Now clear the board. By definition of f of n, by definition of f of n, we have norm of Ti xk less than or equal to n for all I and all k, since each Ti is continuous and xk tends to x, it follows and xk tends to x, it follows that okay. Therefore we have norm of Ti of x, equal to norm of limit k tends to infinity Ti xk, that equal to limit outside, limit k tends to infinity, norm of Ti of xk, that is less than or equal to n for all I, that is norm of Ti x less than or equal to n for all I. So hence x belongs to Fn. Hence x belongs to Fn. Thus Fn is closed for each n. Thus Fn is closed for each n. Now we claim that B equal to linear of 1 to infinity Fn. Suppose B is not equal to 1 to infinity Fn, then there exists x naught belongs to B, such that x naught does not belong to f of n for all n. This shows that norm of Ti x naught is greater than or equal to n for all I, comma, n, and then thus Ti of x naught is bounded in B, which is contradiction to the hypothesis, that T of I x is a pointwise bounded, for each x belongs to B. Hence, B equal to 1 to infinity f of n. Since B is complete, and B equal to union of 1 to infinity Fn, it follows by the Berry's category theorem that there exists an integer n naught, such that f of n naught has non-empty interior. Let us assume that x star is an integer. That is it. Let us assume that x star is an interior point. Of Fn naught. Then there exists a closed neighborhood Sn naught, Sr naught, x star with x star as center and radius r naught greater than 0, such that Sr naught x star f r naught. Then it follows that follows that. Follows that. Norm of PIX less than or equal to N naught. For all X belongs to S R naught X star, and for all I, then S R naught X star minus X star is a closed neighborhood, is a closed neighborhood with origin as center, and radius R naught. Radius R naught. Hence, S equal to SR naught X star minus X star whole divided by R naught is a closed unit sphere. Closed unit sphere. Then each X belongs to S. Then each X belongs to S. SR naught X star. So norm of Ti of X that equal to norm of Ti X1 minus X star whole divided by R naught norm that equal to 1 by R naught norm of Ti X1 minus X star. Clear the board. So here 1 by less than or equal to 1 by R naught norm of Ti X1 plus norm of Ti X star less than or equal to 1 by R naught N naught plus N naught. Since X1 comma X star belongs to SR naught X star, that equal to 2N naught whole divided by R naught for all I. Let capital M equal to 2N naught whole divided by R naught. Then we have norm of Ti that equal to supremum of norm Tix such that X belongs to S less than or equal to capital M for all I. Thus, T of I is bounded subset of B. Bounded subset of B B comma N. This completes the proof. This completes the proof. A simple sequence of unit bounded theorem is given below. So, what we had discussed, students, in the fourth chapter is linear transformation. So, what the properties of linear transformations? Properties of linear transformation. Properties of linear transformations. Properties of linear transformations. What we discussed here, properties of linear transformations, and Bayes category theorem. The Bayes category theorem in the previous year fail analysis. Also, you read that one. Once again, we revised it in operator theory and open mapping theorem and closed graph theorem and uniform bounded theorem. This is the theorem. No? This only we discussed today. And this is four important, most vital theorems. You have to read. Compulsory, one question in the examination you will get. Thank you. Thanks a lot. Thank you very much, all the students.